Hello everyone. Welcome to my channel. My name is Mukku. Today we are going to discuss the intelligence agency of Israel, that is Mossad. What's semiconductor? What is the function of semiconductors? How does semiconductor work? And so on. Introduction. A semiconductor is a material that has an electrical conductivity that falls between that of an insulator and a conductor. Semiconductors are widely used in modern technology, particularly in electronic devices such as microprocessors, memory chips, LEDs, and solar cells. Semiconductor physics. Semiconductor physics is the study of the behavior of electrons in semiconductors. Some key concepts in semiconductor physics include energy bands and band gap. In a solid material, the electrons are arranged into energy bands. The band gap is the energy difference between the highest occupied band and the lowest unoccupied band. Intrinsic and extrinsic semiconductors. An intrinsic semiconductor is a pure semiconductor material, such as silicon or germanium, that has been intentionally left undoped. An extrinsic semiconductor is a semiconductor material that has been intentionally doped with impurities, which changes its electrical properties. Doping and carrier concentration. Doping is the process of intentionally adding impurities to a semiconductor material to change its electrical properties. The impurities used for doping are called dopants. Dopants can create either N-type or P-type semiconductors, depending on whether they donate or accept electrons. The carrier concentration refers to the number of free electrons or holes in a material. P-N junctions. A P-N junction is formed when a P-type semiconductor is joined to an N-type semiconductor. This creates a depletion region near the junction, which has no free charge carriers. Types of semiconductors. There are two main types of semiconductors: elemental semiconductors and compound semiconductors. Elemental semiconductors. Elemental semiconductors are made up of a single element, such as silicon or germanium. Silicon is the most widely used semiconductor material in electronic devices. Compound semiconductors. Compound semiconductors are made up of two or more elements, such as gallium arsenide, GaAs, or indium phosphide, InP. Compound semiconductors can have higher electron mobility than elemental semiconductors, which makes them useful for high-frequency and high-power applications. Fabrication of semiconductors. The fabrication of semiconductors involves a series of complex processes to create electronic devices such as microprocessors, memory chips, and solar cells. The main steps in semiconductor fabrication include crystal growth, wafer preparation, lithography, deposition techniques, and etching and cleaning. Crystal growth. Crystal growth is the process of creating a single crystal from a material that has a regular, repeating structure. In the semiconductor industry, crystal growth is used to produce high-quality single crystals of semiconductor materials such as silicon, germanium, and gallium arsenide. These materials are used as the basis for electronic devices such as microprocessors, memory chips, and solar cells. The most common method of crystal growth used in the semiconductor industry is the Czochralski process. In this process, a small seed crystal of the desired material is dipped into a crucible containing molten material. The seed crystal is slowly pulled out of the crucible while rotating, which causes the molten material to solidify into a single crystal around the seed. As the crystal is pulled out of the crucible, it is cooled using a process called thermal management, which helps to control the crystal structure and prevent defects. The Czochralski process is a highly controlled and precise process that requires careful monitoring of temperature, pressure, and other parameters to ensure that the resulting crystal meets the desired specifications. Once the crystal has been grown, it is sliced into thin wafers using a diamond saw, which are then polished and cleaned to remove any surface defects and impurities. The wafers are then used as the starting material for the fabrication of semiconductor devices. In recent years, new methods of crystal growth have emerged, including techniques such as epitaxial growth, which involves growing a crystal layer on top of an existing crystal substrate. These new methods have enabled the production of more complex semiconductor structures and materials, such as compound semiconductors and heterostructures, which have unique properties and applications. Wafer preparation. After a single crystal of semiconductor material has been grown using crystal growth techniques, the next step in the semiconductor manufacturing process is wafer preparation. Wafer preparation involves taking the single crystal and turning it into a thin, flat disk called a wafer, which is used as the starting material for the fabrication of semiconductor devices. The wafer preparation process typically involves several steps, including cutting. The single crystal is cut into thin slices using a diamond saw. The thickness of the slices can vary depending on the desired application, but is typically around 0.5 to 1.0 millimeters. Grinding. The sliced wafers are then ground to remove any surface defects and to make them flat and uniform in thickness. Polishing. The wafers are polished using a series of abrasives to create a smooth and reflective surface. Cleaning. The polished wafers are thoroughly cleaned to remove any residual polishing compounds, oils, or other contaminants that could affect the performance of the semiconductor devices. Drying. The cleaned wafers are dried using a process called spin drying, which uses centrifugal force to remove any remaining water or cleaning solution. Once the wafer preparation process is complete, the wafers are ready for the fabrication of semiconductor devices. The wafers are typically loaded into a series of processing tools, where they undergo a series of deposition, lithography, etching, and other steps to create the desired semiconductor structure. The entire process is highly controlled and precise, with each step carefully monitored to ensure the quality and reliability of the final product. Lithography. Lithography is a key process in semiconductor manufacturing that is used to transfer a pattern onto a wafer surface. This pattern defines the structure of the semiconductor device being fabricated and can include features such as transistors, interconnects, and other components. The lithography process typically involves the following steps. Photoresist application. A layer of photoresist is applied to the surface of the wafer. The photoresist is a light-sensitive material that will later be exposed to light to create a pattern. Alignment. The wafer is aligned to a patterned mask, which contains the desired pattern. Exposure. The wafer is exposed to light through the mask, which causes the photoresist to change its chemical properties in the exposed areas. Development. The wafer is then developed using a chemical solution that removes the unexposed areas of the photoresist, leaving behind the pattern that was transferred from the mask. Etching. The patterned photoresist is then used as a mask to selectively etch away material from the wafer surface. This can create features such as trenches, vias, and other structures that are required for the semiconductor device being fabricated. Photoresist removal. The remaining photoresist is then removed using a chemical process, leaving behind the patterned structures on the wafer surface. Lithography is a highly precise and complex process that requires careful control of many parameters, including exposure time, dose, and alignment accuracy. Advanced lithography techniques, such as extreme ultraviolet (EUV) lithography, have been developed to enable the creation of even smaller and more complex semiconductor structures. Deposition techniques. Deposition techniques are used in semiconductor manufacturing to add layers of material to the surface of a wafer. These layers can be used to create a wide range of semiconductor components, including transistors, interconnects, and other devices. There are several different deposition techniques used in semiconductor manufacturing, including chemical vapor deposition. CVD. CVD is a common technique used to deposit thin films of material onto a wafer surface. In this process, a gas is introduced into a chamber containing the wafer and is then reacted to form a solid material that is deposited onto the wafer surface. The process can be carried out at high temperatures to enable the growth of high-quality crystalline materials. Physical vapor deposition (PVD). PVD is another common technique used to deposit thin films of material onto a wafer surface. In this process, a material is heated until it vaporizes and is then deposited onto the wafer surface as a thin film. PVD can be carried out at lower temperatures than CVD and can be used to deposit a wide range of materials, including metals, semiconductors, and insulators. Atomic layer deposition (ALD). ALD is a highly precise deposition technique that is used to create extremely thin, uniform layers of material on a wafer surface. In this process, the wafer is exposed to alternating pulses of two different precursor gases, which react to deposit a single layer of material. The process is repeated multiple times to build up the desired thickness of the material. Electroplating. Electroplating is a technique used to deposit metal layers onto a wafer surface. In this process, the wafer is placed in a solution containing metal ions, and a voltage is applied to deposit the metal onto the wafer surface. Electroplating can be used to deposit thick layers of metal and can be carried out at relatively low temperatures. Deposition techniques are essential for creating the multiple layers of material required to fabricate semiconductor devices. These techniques require precise control of deposition parameters, including temperature, pressure, and gas composition, to ensure the quality and reliability of the final product. Etching and cleaning. After the materials have been deposited onto the wafer, the desired pattern is created by selectively removing material using a process called etching. There are several types of etching, including wet chemical etching and dry etching using techniques such as plasma etching. Once the desired pattern has been created, the wafer is cleaned to remove any remaining photoresist or other impurities. Applications of semiconductors. Used as switches and amplifiers in electronic circuits, while integrated circuits, ICs, are used to pack multiple transistors and other components onto a single chip. Power electronics. Semiconductors are used in power electronics to control and convert electrical energy. This includes applications such as motor drives, power supplies, and inverters. Sensors. Semiconductors are used in sensors to detect and measure various physical properties, such as temperature, pressure, and light. Communication devices. Semiconductors are used in communication devices, such as smartphones and radios, to process and transmit signals. Automotive electronics. Semiconductors are used in various automotive electronics, such as engine control units, safety systems, and infotainment systems. Medical devices. Semiconductors are used in medical devices, such as imaging equipment and implantable devices, to process and transmit signals. Overall, semiconductors have become an essential component of modern technology, impacting almost every aspect of our lives. The semiconductor industry continues to evolve and grow, with new materials, technologies, and applications emerging all the time. Future of semiconductors. The future of semiconductors is constantly evolving, with new materials, technologies, and applications emerging all the time. Some key areas of focus for the future of semiconductors include new materials and technologies. Researchers are exploring new materials and technologies that could potentially replace or supplement traditional semiconductor materials. For example, graphene is a promising material for use in high-speed electronics, while nanowires and quantum dots could be used for building tiny sensors and other devices. Emerging applications. As technology continues to advance, new applications for semiconductors are constantly emerging. One area of particular interest is quantum computing, which could revolutionize computing by using the principles of quantum mechanics to perform calculations that are impossible with traditional computers. Challenges and opportunities. There are a number of challenges facing the semiconductor industry, including the increasing complexity of semiconductor manufacturing, the need for new materials and technologies, and the increasing cost of research and development. However, there are also significant opportunities for growth and innovation in the semiconductor industry, particularly as new applications and technologies continue to emerge. In conclusion, the future of semiconductors is constantly evolving, with new materials, technologies, and applications emerging all the time. The semiconductor industry faces a number of challenges, but also significant opportunities for growth and innovation. The continued development of new materials, technologies, and applications will be key to the future of semiconductors and their role in modern technology. Where does India stand in the semiconductor market? India currently imports all chips, and the market is estimated to touch $100 billion by 2025 from $24 billion now. However, for the domestic manufacturing of semiconductor chips, India has recently launched several initiatives. The Union Cabinet has allocated an amount of 76,000 crore rupees for supporting the development of a semiconductors and display manufacturing ecosystem. Consequently, a significant number of incentives would be provided to design companies to design chips. India has also launched the scheme for promotion of manufacturing of electronic components and semiconductors, specs, for manufacturing of electronics components and semiconductors. In 2021, the MeitY also launched the Design-Linked Incentive (DLI) scheme to nurture at least 20 domestic companies involved in semiconductor design and facilitate them to achieve a turnover of more than 1,500 crore rupees in the next 5 years. India's own consumption of semiconductors is expected to cross $80 billion by 2026 and to $110 billion by 2030. Conclusion. In summary, semiconductors are a critical component of modern technology, with applications ranging from microprocessors and memory devices to solar cells and LEDs. Semiconductor physics involves the behavior of electrons in semiconductors, including concepts such as energy bands, doping, and p-n junctions. There are two main types of semiconductors, elemental and compound, and semiconductor fabrication involves processes such as crystal growth, lithography, and deposition. Looking towards the future, the semiconductor industry is constantly evolving, with new materials, technologies, and applications emerging all the time. While the industry faces challenges such as increasing complexity and cost, there are also significant opportunities for growth and innovation. Semiconductors have a significant impact on society and the economy, with advancements in technology leading to improved communication, computing, and energy efficiency. As such, the continued development of semiconductors will play a crucial role in shaping the future of modern technology and its impact on our daily lives. Thanks for watching my video. Please subscribe, share, like, and comment.